On the bench today we have the Fluke PM3394A 200 MHz oscilloscope. This is both a analog and a digital oscilloscope, and it has 4 channels. I've always wanted one of these, but I never thought I'd get one, but now I own one. This particular one has got a couple of faults. One is really minor. The backlight illuminator isn't working. I'll fix that. But the other one's more concerning. What I'm seeing on the CRT is a pulsing or a glitching. The CRT display is contracting and then it's glitching and stretching out. It's pulsing at a slow frequency that is proportional to the brightness of this display. In effect, it's proportional to the CRT beam current. Now, I don't know why it's doing that, but it's possibly because there is a component that is on the verge of failure. I want to find out what's causing that fault, because if a component is about to fail, there's a reasonably good chance that it could take other components out with it when it does finally fail completely. So I'm going to start doing visual inspection to see if there's anything cooked, hot, burnt, and then I'll look at the power supply, because the symptom that I'm seeing could possibly be caused by one of the outputs of the power supply glitching up and down. I'm going to start by testing the power supply, and based on the results of that testing, then I'll decide what to do next. When I needed to fix the power supplies for my Philips PM3070 oscilloscope, the manual suggested I make a dummy load for the power supply, and this is what I needed. It was pretty straightforward to make up. There's a socket here which went off to a ribbon cable to the scope itself, and it was easy to connect. So when the manual for the Fluke PM3394 suggested I make a dummy load for the power supply, I thought I'd do that. But as it turned out, I needed something quite a bit more substantial. And this is what I've come up with. And the features of this is that it has all the resistors that load up each power supply. It has the connector, the socket here, that is a substitute for the backplane connector, which means that the power supply needs to be in a very specific position relative to the dummy load. I've got guides here for the PCB, so that when the PCB is plugged into the socket, that it can't flop backwards and forwards. And I've also got a couple of fans here which cool both the load resistors and also, and perhaps more importantly, cool the power supply. So how does this work? Well, we take the dummy load, we slot it in to the guides, it goes down and presses on and plugs into the connector, and there it is, all ready to go. Right, I've got everything set up ready to apply power to the power supply for the first time in its dummy load. And so to do that, I've got the power supply plugged into its dummy load. I've got a couple of fans there which I'm not powering up initially, because I'm only going to apply power probably just for a few seconds. I've got a high voltage probe there which is at the moment plugged in to the CRT output, and the purpose for that is that the way that this power supply is connected up, the power for the voltage multiplier goes through the edge connector. So if there's no connection on the dummy load of the edge connector, then there's no supply for the voltage multiplier. And if there's no supply for the voltage multiplier, then there shouldn't be any output voltage on the CRT connector. And that's what I'm looking for. That is a safety feature of the power supply, and that unless I make that connection in the dummy load side, there's no high voltage output, which is absolutely desirable. The first test that I'm going to do is to look at the voltage output from the high voltage probe to ensure that that is actually zero. If it isn't zero, I need to look at that immediately. And the other reading initially will be the total power consumption. And for this power supply on the dummy load, it should be about 115 watts. If I see more than 115 watts, then I'll cut power immediately. So the plan is to apply power for a few seconds, long enough to ensure that the voltage multiplier output is zero, and also to look at the total power used by the power supply connected to the dummy load is close to 115 watts. I'll turn the supply off, and then one by one I will go through and check each of the DC power outputs on the power supply. I'll make a connection, turn the power on, check that the voltage is about right, and then switch off. Move to the next power output, connect up, switch it on, measure it, make sure it's right. And from that point, I will then leave the power supply on, turn the fans on, and check for voltage ripple on each output. The aim is to detect any fault early and hopefully minimize the damage occurred if the magic smoke is released. I'm all ready to apply power for the first time. If I've got the dummy load connected up correctly, there shouldn't be any magic smoke. So let's see how that goes. 1, 2, 3. 14.9 watts, that's too low. No voltage on the output of the high voltage probe. I can also hear a squealing sound out of the power supply, so something isn't right. Let's investigate. So when I put the power supply onto the dummy load and apply power, I'm only getting 16 watts. Clearly something is wrong. So where do I start? Well, given that the power supply came out of an oscilloscope that was 99% operational and had what appeared to be a small fault, and it's not working at all when I put it into the dummy load, then I have to start off with the assumption that there's a fault in the dummy load that I've produced. This circuit diagram is one of 3 sheets in the service manual. That includes the edge connector that is the interface between the power supply and the dummy load, and includes all of the pinout. What I think I need to do is start by double checking to make sure that the pinout in the circuit diagram matches the pinout of the dummy load that I have. When I look closely at the circuit diagram that included the pinout of the edge connector, I found a problem. Pins A26 and C26 are shown as plus 58 volts. When I look at another sheet which includes a diagram of the pinout of the edge connector, the pinout shows that A26 is 5 VA, which I read as 5 volts analog, and pin C26 is plus 58 volts. This is different to what is shown in the other page on the circuit diagram. So maybe this is why the power supply is not doing what it's supposed to do. When I was making the dummy load, I was really careful to check to make sure that the dummy load was wired up correctly. During the process of checking, I found that discrepancy between the pins A and C26, and I checked with the power supply hardware to see what was wired up and compared that to the 2 versions in the circuit diagram. So I'd found the error in the circuit diagrams and accounted for that when I connected up the dummy load. So that wasn't the problem. There was something else. So I decided I need to go through and recheck and double check everything, and as part of that I created a color-coded spreadsheet which detailed all the pin connections, which was intended to highlight any discrepancies and errors, because I was still going on the assumption that the dummy load had a fault that I'd add in there and that the power supply was still okay. So when I'd completed the color-coded spreadsheet, I then went through and tested the pins on the actual dummy load to ensure that the resistances on each pin were correct. And I found one that wasn't right, and that was the power HT output. The connection for the power HT is on pin C32, and in the circuit diagrams it's not shown with all of the other connections, it's shown on a different sheet. It's an output that also has an input into the power HT circuit. The power HT signal indicates there's a power failure, but it also enables the HT output. I found that I had accidentally connected the power HT output to a resistance which was driving it to a value that disabled the HT output voltage. But the dummy load already configures the power supply not to produce a high voltage HT output, so it shouldn't have any significant effect on the load that the power supply draws, or doesn't in this case. It was a fault, an error in the way that I'd wired up the dummy load. It should not have caused any issues with applying power with the dummy load connected. Right, I'm all ready to have another go at applying power. I've fixed up the one fault on the dummy load that I found, which I don't believe will make any difference at all, but we'll soon see. So that fault disabled the power supply to the voltage multiplier, but the voltage multiplier is already set up through the dummy load to not have the 58 volt supply. So disabling a voltage multiplier circuit that has no supply shouldn't make the slightest bit of difference. So what have I got here? I've got my mains power meter here, which will tell me the voltage and current and power in watts. I've got my probe set up on the high voltage output on this meter here, so that should stay 0. And I've also got the gold star meter here set up to monitor the -12 supply. And the reason why I'm monitoring the -12 supply is because the voltage supply protection monitors the -12 volt supply on the basis that if any of the supplies is overloaded, then that will be seen on the -12 volt supply. If one goes down, they all go down. My expectation is that the power supply will instantly cut out and the power consumed will drop to about 16 watts, which is what it was before. I shouldn't see a voltage from the high voltage multiplier because that is disabled and has no power supply. Right, this is the second time that I'm applying power. So 1, 2, 3. Got 100 watts. Right, so I was wrong. 105 watts, which is normal. And I've got -12 volts on the power supply. So the error in the dummy load circuit definitely appears to have affected the power supply. The voltage output from the voltage multiplier was 0, which is good. That's what I was looking for. and I had minus 12 volts on the multimeter here, which is good. So now what I'm going to do is I'm going to go through and check each power supply output to make sure that it's the right value, and look at the ripple current to ensure that the filtering is working correctly. And I'm going to switch the fans on to do that, to keep the dummy load and the power supply cool while I'm doing the testing. So now that I've been able to switch the power supply on and prove that there's no output from the voltage multiplier, and also prove that the power supply has not decided to trip out, I'm going to quickly go through and measure the individual voltages. I've got a voltmeter here which will measure down this side, and I've got this voltmeter set up here so that I can quickly go down the sequence of power supplies outputs down this side to check that they're the right value. All ready to apply power for the second time today. So let's start with the minus 5.2 volt supply. So when I switch on, I should see minus 5.2 here, and I should see somewhere around 105, 110 watts here. I've got the fans running, so I don't have to worry about overheating anything. So let's try this out. 1, 2, 3. Right, I've got minus 5.87 volts, so minus 5.1. I've got minus, oops, let's change the scale, minus 61.4, so that should be minus 58, but that's close enough. We've got plus 12, 12.3, yep, happy with that. So let's go down the other side here. I should have, on this meter, I should have minus 18 volts. I've got minus 18.02, minus 5.2 volts. I've got minus 5.3, plus 5 volts, yes. I've got plus 18 volts, 17.7 volts, close enough. Plus 58 volts, well, it's plus 60.8, so close enough. And a 10 volt reference, 9.88. Right, so the power supply seems to be working as it should do. Now I'm going to let this, I'm going to let the power supply run for a while, because the fault that I'm seeing appears to be heat dependent. So I'm going to let it run and see if the fault that I saw on the oscilloscope exposes itself in the power supply when it warms up a bit. I've got the oscilloscope set up to monitor the minus 12 volt supply, and it is as smooth as silk. The oscilloscope is set up at 50 millivolts per division, and the noise is low. There's no glitches or no 50 hertz that I can see in that noise. It's all looking good. The way that the power supply is set up, if there was any problems or glitches on the other supplies, they would show up in the minus 12 volt supply. So if there's a problem with the one, there's a problem with all, and I'm not seeing any problems at all. This has been running for about 15 minutes or so, and there is no indication at all of any fault or deficiency in the power supply. So the fault that I've got in the oscilloscope has to be in the oscilloscope itself and not in the power supply. And that's the advantage of having a dummy load, is that it isolates the power supply so that I can isolate where the fault is, and there's no indication that there's any fault in the power supply. So what I'm going to do now is I'm going to put the power supply back into the oscilloscope and start looking for a fault in the oscilloscope itself. That's probably going to be quite difficult to do because I don't have an extension card. So yeah, let's see how that works.